Hey guys, I got one more special case of kinematics for you here. This is called the level ground problem. It only works on level ground. So if you were like standing on a football field and you kicked the ball and it went up, 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 and it came down and it landed on the same level, on the same altitude, the same height that it was launched from, then we'd be talking about a level ground problem. All right, so that's where we're headed today. Here is a little picture of one of those. You can see that the object here, this little gray ball, could be a cannonball, could be a football that got kicked, it could be a frisbee, it could be a car that jumped off of a ramp, a bicycle, it could be just about any kind of object that gets propelled up into the sky and it comes across. And most importantly, it was launched from this height and it lands at that height. Okay, that's the level ground right there's the level ground going on that we're talking about. So we want to talk about that problem. Remember how in the cliff problem we had to break apart everything in the x direction and in the y direction? Well, that's going to be exactly the same here. So I've already started that up here. This is going to be our x direction variables and our y direction is going to go over here. But we need to fill in some numbers on that. Now, I'm going to walk you through this process of deriving this formula and show you how to use it. But in the end, what we want is to know what the initial velocity is and the angle. Given V0 and theta, then we'd like to be able to find out several things. How long it's going to be in the air. How far does it go to the right? So I'm going to call those find T, the time in the air, and R, which is going to stand for range here, how far it goes. All right, so that's kind of the two parts of this thing typically, and I'm going to show you how this works. First thing though that we have to do is to cook up the components of this thing in the x direction and in the y direction. All right, and this is very similar to what we did on the last thing. They're going to give us a V0. So down here, I'm going to draw V0 going that way. And there's some angle of inclination there, theta. All right. I want the components of that. So it's no real big surprise when I come right here and I draw the x component. And I see that that's the adjacent to the angle. So V0 x is going to be equal to V0 cosine theta. And similarly, I want the y component, and that's going to fall right here, and be that side. It'll be opposite the angle of inclination. So I get V0 y equals V0 times the sine of theta. All right. So that's the first thing. I'm going to go ahead and put those up here. This would be V0 cosine theta. This would be V0 sine theta. Going back to the definitions of cosine and sine right there. A sub x, a sub y. I need to break those apart. A sub x, of course, is 0. A sub y is 9.8 meters per second squared. This is gravity. And gravity does not pull sideways, so I don't have anything there. We're not doing air resistance. We're not doing a rocket that's continuously propelled. It's a cannonball that gets shot out. It's a football. It's a golf ball that gets hit. And once it's hit, it's not moving any faster in that direction. Okay, gravity will work on it, but the other thing won't. Now, the other thing that I have to be real careful about here, and we had to do this with the cliff problem too, is to think about our directions. So let me just come in here, and especially in the y direction. All right, everything's to the right for the x direction, so that's not really an issue. But right here, my initial velocity is up, and the gravity is down. You can handle that any way that you want to, but I'm going to come in here with a coordinate system and draw a vertical coordinate system like so, and everything that points up needs to be one sign and everything that points down needs to be the opposite sign. I'm going to call up positive, and down then will be negative. And that means when I write these things up, then the V0 sine theta, the y component, is up positive and the gravity is down negative. Alright, so those are the variables that we need to worry about when we do this. Let's see how that comes into play with the problem. There's several steps that we need to do here. I've already got the variables up there like we just had, so that's all ready to go. 3 little steps here that are going to give us 2 formulas to work on this. And just like with the cliff problem, I've got some stuff that goes on in the y direction. Everything over here on the left side of the screen is y direction variables and formulas. And over here, once I've got that figured out, then I can come back and get the x direction stuff over here. Alright, so that's the game plan. And I'm going to do these generically, not put any numbers in, because I want a formula that's going to work every time for this. I don't want to have to do this every time. Let's do it once and be done. Find the time to the top. When I think about this ball right here, it starts right here, and it goes up, 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 and it hits this point right there, and it stops going up. Its final velocity in the y direction is 0. It is no longer going up. It stops momentarily there. Down here, my V0 y, we've already said, was equal to V0 sine theta. Okay, we've already said that a sub y is negative g. Let me just put, yeah, I got negative g there instead of negative 9.8. If you leave it g, then, you know, if you go to the moon or to Mars or something, then you could just put in the right number and you wouldn't have to redo this. So let's leave it g here. And what we're looking for, you remember, was the time. So with those variables right there, it shouldn't be too hard to pick a formula that has V0, V, A, and T. I've got one of those. So we're going to come in here and write down our our velocity formula. Looks like that, right? I'm only thinking about the y direction, so I'm going to put my little subscripts in if it'll let me. And that looks fine right there. We're looking for the time, so I'm trying to solve this for t. I need to subtract V0 y from both sides. And I need to divide by a sub y. And that's going to be equal to t. The v sub y is 0, so let's just cross this guy out. And then I need a negative V0 y. I come over here and I look at my V0 y, and that is positive V0 sine theta, but I need to negate it here. So I'm going to put in a negative V0 sine theta, negative from the formula, positive in the variable up there. Negative times a positive is a negative. Downstairs I've got negative g, and that's going to be equal t time to the top. Okay, the negative signs cancel. It's just going to be positive like that. All right, so that's the first step. Second step is to double that time. If it takes that much time to go from here to there, it will take exactly that same amount of time to reach the other side, you know, from the top to the here, or twice that time to travel the entire distance. So all we have to do here is come in and say 2t. I'm actually going to give it a new name. Let's call it capital T here. Would be twice what we just got. 2v0 sine theta divided by g. That is the time in the air right there. And what's nice about that formula is that I don't have to break apart the components, right? It's already done for me. It's already built in there. I don't have to worry about the coordinate systems. You give me V0 and theta, and I can tell you how long it's going to be in the air. All right, you just put the numbers in. We'll do some examples with this in just a second. But that's the first formula that I wanted to cook up right there. The second formula comes in the third step right there. Find the x distance. How far does this thing go? Well, over here, we're looking at the range. So I'm going to put a little dot right here where this thing lands on level ground and call that R. I'd like to know how far away from the starting point that is. And this distance right there. If I shoot something up at an angle, throw a snowball up at an angle, where's it going to land? Is it going to hit the guy in the snow fort or not? So we have an x distance formula. X equals v naught x t plus 1/2 a sub x t squared. We know that's the right formula because I've got the v naught, I've got the a, we just found t, right? So I got that one. And we're looking for x, and the formula that has those four looks like that. All right, so we're good to go here. And you know what? I just circled all the wrong ones, didn't I? Yeah, I should have been over here on the x side, not the y side. All right, so 1,000 apologies here. We're looking at this side with our x variables over here. And we just found time, and we want to know x, which we're going to call r now. Okay? All right, so that looks okay. Let's go ahead and replace the x with r to stand for range. I see that v naught x is actually v naught cosine theta. This time, here's the time that it spins in the air. So I'm just going to drop that in. Look like that. And all of this stuff, the second term, goes away because a sub x equals 0, right? Half times 0 times t squared. All that's going to cancel out. I'd get a plus 0 over here. That doesn't do anything, so just ignore it. All right. I'm looking at this, wondering if there's any way to clean that up. And I see that I'm multiplying a v naught here times a v naught there. So that would be a v naught squared. You got that g on the bottom. What's left? I got a cosine, I got the 2, I got a sine theta, and there's a little trick that we can pull here. That is a trig identity. The trig identity, a trig identity, is a little trick that we can pull with trig functions to simplify them, to cook them down to something smaller. But there is a particular trig identity that says anytime you have 2 sine theta cosine theta, you can rewrite that as sine of 2 times theta. All right, so I'm gonna do that right there. You can look up trig identity tables, and that will be on there. That's a well-known trick that we do in mathematics. But once I've done that, then I get v naught squared. All of this stuff right here is just going to get replaced with the sine 2 theta. And I like to put the 2 theta in parentheses to remind myself that I'm really taking the angle and doubling it. This is called the double angle identity. I need to, if it's a 30-degree angle that I launch this thing at, I need to come in here and say 2 times 30, or 60 degrees, and then put that in there. It's over g, like that. So that's kind of the cleanest way to write that. All right, we've got these two formulas: t, the time in the air; r, the range. I need to remind you one more time that this is the level ground problem, and it only works on level ground. Okay, so don't go trying this on a cliff problem. You can see right here, if the shot kept going down, 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 that would take more time. This would be wrong, which would mean that this would be wrong. Okay, or if the thing hit the mountainside up here or something, it's not going to go that full distance, so the range would be, if something stops it before it gets there, it's not going to be the same distance. So this only works on level ground, and be careful about that. It is a special case. Here, for example, we've got a football. It's sitting on the ground. We're going to kick it. It goes up at a 37-degree angle, and we kicked it at 40 meters per second. I don't know if that's a realistic number for kicking a football or not. It sounds kind of high, actually. But this is theta. This is V naught. That is all that I need. Okay? I can come in here with my time formula, and T equals 2 V naught sine theta over G, and I drop my numbers in, 40 meters per second here, times the sine of 37 degrees, and I divide that by G, which on Earth would be 9.8 meters per second squared. All right, that is the quickest, easiest way to do this. We've derived it once, so we believe it, and we just put the numbers in, plug and chug right here. 2 times 40 sine 37. Do make sure that you close up the parenthesis right there, and then divide by 9.8. All right, but that what was this? A football is going to spin 4.9 seconds in the air. Okay, and we're done. Again, we don't have to break apart the components of the initial velocity. We don't have to worry about a sub x and a sub y, or we don't have to worry about up and down and the positive and negative. It's already built into the equation. It's all done for you. You just drop those two numbers in. On the other hand, if I want the range, how far away from the, what do they call that little thing in football where you put it on the tee, maybe? You put it on the little cup thing on the ground. I could come in here. If I want the distance, I see that it's V naught squared sine 2 theta. I'm dividing that by G. I've got V naught, I've got theta. We're ready to go with this thing. 40 meters per second. That gets squared. Here's a sine of 2 times 37 degrees. Remember, we're doubling the angle right there. And we divide by 9.8 meters per second squared. All right? And I don't know what that is, but my calculator does. So let's see what it says. 40, hit your squared button, sine 2 times 37, and close that up right there. Divide by 9.8, and that's 157 meters. Okay, the 40 meters is probably a little too big for a real football game, but is that what I can't remember. Yeah, 157. Okay, that sounds kind of excessive, but you know, that's the numbers they gave us, so we just put them in and go, okay, whatever you say, boss. All right, that's pretty easy, pretty painless. It only works on level ground, but you've got those two formulas. You plug your numbers in, you're good to go. All right, here is another example. A motorcycle tries to jump a 150-meter wide canyon, launching at a 37-degree angle and moving at 40 meters per second. So this problem would be really easy to come in here and say, well, gee, you got yourself a canyon. That's not level ground. But see how it lands at the same height that it started at? Here's your motorcycle right here. Come on. The motorcycle's up on the top of this canyon wall, and what a crummy picture. And it goes up and back down, and it's on the same level over here. It's not quite level ground, but it's at the same height, right? And so that's what matters. Whenever the launch point and the landing point's at the same height, then we're good to go here. And I would assume that they mean for this to be a level ground problem. If they didn't want this to be a level ground problem, then they would have had to tell me the height of the cliff, and they didn't do that. Right? It's 150 meters wide, and they didn't give me anything about the depth. If I needed that, you know, to consider how long it would take to fall down here or something, they would have had to tell me that. They don't always say, hey, this is a level ground problem, but this would be one where we could jump in and say, well, let's use the level ground problem, and that'll tell us how far this guy can go at that speed, at this angle, and we'll see if he survives or not, okay? With the football problem right here, they didn't really say that it was a level ground problem, right? We just kind of assumed that. We go, well, yeah, football gets played on level ground. And they didn't really explicitly tell us that, all right? But usually with these, you can tell pretty quick, yeah, it's a football. It's going to be on a level field. Here they didn't give me the height of the canyon, so it must be the same thing. I'm going to assume that it's level ground. Does that make sense? Okay. And I could do the same thing here. I could come in and I could say the time is 2 times 40 meters per second times the sine of 37 degrees. Divide that by 9.8, and I could say the range is 40 meters per second. That gets squared. Sine of 2 times 37. Divide that by 9.8. Okay. I don't know that the time's really important here. Let's check the range. See if he made it here. I'm kind of worried about him now. 40 squared sine 2 times 37. Are these the same numbers we just used? Might be. Divided by 9.8. Yeah, 157 meters. Okay. So, does he make it? Yeah. Yeah. This guy sails through the air 157 meters. He lands with 7 meters to spare. And he does, you know, he gets to go home at the end of the day here. Okay. So I don't know why I used the same numbers. Apparently I copy-pasted and forgot to change the numbers there. All right. Anyway, you get the idea. It works for a football. It works for a motorcycle. It works for a bullet. It works for a water balloon, a pumpkin off of a trebuchet. It works whatever you want to consider here. Now, this is kind of one more thing that you can do with it here. And remember that motorcycle that we just had in the last problem? He only went 157 meters. He steps up, he moves downstream a little bit, and all of a sudden the canyon is 200 meters wide. Last time he only went 157 meters, so he's not going to make it on this one. He needs to change something. Apparently his motorcycle will not go any faster than 40 meters per second. So that's fixed, right? I can't change this. But what I could change is that angle. So we'll draw the canyon again. Last time we went up at a 37 degree angle. And that's gonna crash him on the wall down here. He's not gonna make it far enough. He's gonna miss the far side and fall into the hole. That's bad. So he needs to do something here, and the something that he can do would be to tilt his ramp up a little bit more, like that. I can't change V0, but I could change the angle. So we'd be interested in finding that angle, or he would be, you know, how steeply do I need to tilt this thing up to clear this thing. All right. So what I'm going to do is to take the range formula here. I know the range is 200 meters. I know the V0, and of course I know G. I want theta. So see how that formula, if I rework it, solve for theta, will give me that number. All right, let's do that right here. I've got R equals V0 squared sine 2 theta over G. I want to solve for theta, so let's get rid of this divided by G first. I'll multiply both sides by G. Cancels on the right, pops up on the left. Looks like that. Okay. Next up, I'm going to divide by V0 squared. That'll leave me with sine of 2 theta. I don't want sine of 2 theta. I want theta. So I got to get rid of sine. Let's arc sine the left. That'll leave me at 2 theta. Okay. I don't want the 2 there. So last step would be to divide by 2, or maybe another way to say it would be to multiply both sides by 1/2. Okay, that's a pretty handy formula to have on tap too. You may want to put that on your card where it's already solved for theta. You can see you can get it pretty easily here out of the thing. If you want the gory details about what we did on each step, I can put those in here. I'll put them in red so it looks different. The G canceled right there. Multiply both sides by G. Of course, it's not going to like that at all. I'm going to put it out front here. Can't even do that. Okay, so we'll put the G here. Multiply both sides by G. That turned into this. Next up, I needed to get rid of the V0 squared. So if I divide by V0 squared on the right, and I do it on the left, then it turns into that. I want to get rid of the sign. This is where we bring it over to the other side. You can call it inverse sine if you like. I don't like that, but we didn't invert anything. But we've got the arc sine of all of that stuff that was on the left. That's equal to 2 theta. And then lastly, right here, I multiplied this side by half. Half times 2 is 1. Cancels, goes away. I'm left with theta, but I got to do it over here too. All right? So not too hard to get that thing out, but maybe you just want to go ahead and put it on your card and not worry about it. All right, let's see what happens when we put in the numbers. I got 1/2 times the arc sine. The range is now 200 meters. You could add a little bit more if you were worried about him just hitting the edge or something. Here's G, 9.8 meters per second squared. His velocity is 40 meters per second. And please don't forget to square that one. See how it's right there in the formula? The V0 has to get squared. It was squared up here. It's still squared when you divide both sides by it. All right, that's the easiest thing to mess up, and what people usually forget and get a funny thing. In fact, let me just show you what happens when you do that. I'm going to put in a 0.5 for the 1/2. Arc sine, I hit second sine. Right here I go 200 times 9.8 divided by 40. And I'm going to not square it here on purpose. I'm doing this wrong, so don't do this. But that's what happens. Okay? It blows up. Effectively here you're going to have 200 times about 10 is 2,000 divided by 40 is 50. You're saying, go get me the angle that has 50 for a sine. Well, there is no angle that has anything greater than 1. All right? It only goes up to 1. Sine's always trapped between -1 and +1. So that's not going to work. All right? But what I need to do here is do all of this and then square that the initial velocity there. And apparently it still isn't going to make it. Picked some bad numbers, didn't I? Let's see. Go to... Yeah, this guy's just going to die no matter what. All right? He can't jump 200 meters. Who made this problem up? 40 meters per second is not fast enough at any angle. There's a little interesting thing that happens here. If you want to go as far as you possibly can, the best angle to go at would be a 45. Why is that? Because when I come in, I put a 45 right here. 2 times 45 would be 90. Sine of 90 is 1. That's the biggest thing I ever get out of this. So the maximum range that I'm ever going to get out of one of these equations is when that sine is equal to 1. That happens when this is a 45. So if I just take V0, which is 40, and square that, divide by 9.8, the maximum range this guy is ever going to get is 163 meters. All right, so this is just a bad problem. I picked some bad numbers. Sorry about that. That's just the way these things happen sometimes. So I'm going to put down here something like not possible. Needs to go faster. It's kind of like if I threw a snowball and I tried to hit Miami, Florida with it or something. There's just no way that I can throw a snowball fast enough to make it to Miami. You know, I might could put it in a cannon or a, something and make it go faster, but this guy trying to jump the cliff, it just isn't gonna happen. Okay, but that process will work as long as your thing will. I guess we should do one more here where it will work. So I'm going to try in this blank space here just to say find theta if the range is, let's pick something kind of, oh, I don't know, 20 meters, and V0 equals, oh, I don't know, 7 ought to do, I think, 749, yeah, okay, meters per second. All right, so here's a snowball. I can throw a snowball 7 meters per second, and if I'm right here, hunkered down in my snow fort, and my buddy's over here, he's such a good friend that I want to hit him in the head with a snowball. I need to know what angle to launch this thing and catch him right there. Okay, I know the speed that I can throw at her. Maybe I've got one of those slingshot things, you know, that you're supposed to put water balloons in and launch them. Maybe we pulled one of those out of the garage, and we're using that. We know how fast it sends it, but I need to aim up or down. If you had a pistol or a rifle or something, I can't control the initial velocity other than by putting more powder or a lighter bullet or something like that. So the only thing I can do is aim up or down. If it's a bow and arrow, I aim the thing up or down. I need to be able to find that angle to hit a target a certain distance away. So this is that problem. And that formula that we had there was theta equals 1/2 arc sine Rg over V0 squared, like that. Let's put the numbers in here. This should work out fine, I think. Oh, got a 20 times, and that's in meters. That's my range. The G, 9.8 meters per second squared, and I'm dividing that by 7 meters per second. That still ain't going to work, is it? That would be about 200 over 49. That's still greater than 1, so I'm just doing a real bad job today. Let's crank this up to 17, because I really want to hit this guy here. Okay? All right. There's another point I want to make with this, is just why I'm going to the trouble of picking some more numbers. Still not doing a very good job of it, but 0.5 second sine 20 times 9.8 divided by 17. I forgot to write the squared, but I'm not going to forget to square that down here. 17 meters per second squared, that's critical. So here's my squared. Hit enter. A 21.4 degree angle does the job. Okay, so I've got a solution there. Now the reason I wanted to wade through this problem one more time was because there's actually a second angle that works. I could aim this thing way high up in the sky, and it could go up, 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 and come back down. And that second angle there, let's call it theta 2, will also work. There are two angles here that work. The 21.4 degree angle works, and there is a second angle. This second angle is really easy to find because it is the complement, the complementary angle to the first one. If I take 90 degrees and subtract the first angle, then I get the second angle that works. And so we're looking at 70, 69, 68.6 right there. Would also take care of the problem. All right, either one of those would be fine. In modern artillery, of course, you've got you know, howitzers and tanks and stuff that kind of fire along that red line, but then you've got mortars that send a shot way high up into the sky and come back down from above. And there's advantages, disadvantages to both of those, but you want to know all your options. So either one of those angles will work. It's always the complementary angle because of the nature of this 1/2 arc sine right there. And maybe it would be better to come at it this way. If I go back to the original range formula, and write that, the V0 is a constant, right? That's the speed of the bullet or the snowball or whatever, and we're saying that's fixed and I can't do anything about that. G, that's gravity of Earth. I certainly can't do anything about that. So the part that I'm interested in is this sine 2 theta. And watch what happens right here. When I come in and I put these two angles in, if I say give me the sine of 2 times 21.4, that would be this first angle, then I get 0.679. And if I say give me the sine of 2 times the second angle, 68.6, I'll get exactly the same thing. Okay, so that's why this works, because when you double the angle, both of those will give you that same value of sine, and that get multiplied by the initial velocity squared and divided by the acceleration due to gravity, and you've got the same range on it. All right. Anyway, that's enough of that for today. That's the level ground problem. It only works on level ground, so please be careful about that. Don't try to apply this to a cliff problem or anything else. But if it's a level ground, or if you can say, yeah, I'm going to assume that's level ground because they didn't give me anything about the height or the time that it takes to go from here to up some point up in the air or something, then you use this and it's pretty easy, straightforward. All right. Thanks bunches. Y'all be good.